This presentation is on the production of polypropylene from propylene. Polypropylene is produced from propylene, which is a byproduct produced from crude oil distillation. Polypropylene is a semi-crystalline thermoplastic which has a definite order of arrangement of its macromolecules in its structural chain. It is a vinyl polymer with methyl groups on every other carbon atom in its chain. The arrangement of the methyl groups on the chain of polypropylene determine its physical and chemical properties, specifically its isomers. As you can see in the diagram, isotactic polypropylene and syntactic polypropylene are two isomers of polypropylene, which are collectively called stereoregular isomers. For the isotactic variant, it has methyl substituents arranged on one side of its chain. However, with the syntactic variant, it has methyl substituents alternating between opposite sides of the chain. Since its discovery in 1954, polypropylene has been extensively used in many manufacturing industries because its physical and chemical properties make it a suitable material for many applications. These properties include its lightweight nature because of a relatively low density of 0.9 grams per cm cube. It has a melting point range from 160 degrees Celsius to 171 degrees Celsius for the isotactic variant of polypropylene. It has a high heat distortion temperature, high flame resistance, and retains its physical and chemical properties across a wide temperature range, experimentally determined to be 10 degrees Celsius to 110 degrees Celsius. It has excellent chemical resistance to acids, bases, a good resistance to aldehydes, aliphatic hydrocarbons, ketones, and however has limited resistance to aromatic halogenated hydrocarbons and oxidizing agents. All these unique sets of properties of polypropylene are retained, making it the go-to plastic material over many other plastics because of the cost involved in producing it, which is relatively low. Polypropylene is applied in many fields of manufacturing, from the packaging industry through to textiles, automotive, in medicine, and in many other fields of manufacturing. Production of polypropylene involves many key stages, starting from the feedstock preparation and ending in the pellet storage and distribution. This process flow diagram shows the production of only the isotactic or syntactic variants of polypropylene, which utilize a Ziegler-Natta catalyst. It starts from the storage of the propylene, which is a polymer grade, and this feed is then pumped through to the degasser, where dissolved oxygen in this feed is expelled. It then moves through to a heat exchanger where it is cooled and then fed to the feedstock dryer to remove any excess moisture. The feed then goes through the pipelines through to the polymerization reactor, where reaction conditions are kept relatively constant using instrumentation such as pressure gauges, pressure sensors, valve controls, and many other instruments. In the polymerization reactor, catalysts are fed by way of proportionation pumps, which pump catalysts which are in a slurry form into the polymerization reactor to ensure the relative quantities of reactants needed are present at every given point in time. A temperature is highly controlled when the gaseous polypropylene is then passed through the pipeline and recycled through to a cooler, which reduces the temperature to keep reaction conditions at optimum level for the highest yield possible. The polypropylene produced from the polymerization reactor comes out in a fine like powder form, which then passes on to the separators, where gaseous polypropylene is then recycled back into the polymerization reactor. The fine powder is then separated and then moves on through to the purge bin, where nitrogen and steam are supplied to remove any excess monomers in the feed. This then moves through to the blender where additives are added, such as pigments, antioxidants, and other compounds, and then it's passed through to the extrusion unit over here, which handles the solidification and pelletization of the feed. This is then moved through the pellet form of the polypropylene, which is now obtained, is then passed on to the conveyor, through to the conveyor where it is moved on to the storage unit. This simple process flow diagram clearly shows the highly important stages needed in producing polypropylene.
Okay, a typical plant layout has many of these sites: feedstock storage, main plants, quality control rooms, products, and these other things. The polypropylene plant relies heavily on advanced computer system and digital infrastructure to operate efficiently, ensure safety, maintain product quality, and optimize production. There are a lot of IT needs in the plants that are required to for efficient function. It contains automation. Input and output systems are very crucial in the IT needs. These input systems consist of sensors, thermocouples and resistant temperature detectors, pressure transmitters for to ensure safety within pressure ranges, face recognition for security access control and staff identification, barcode scanners for tracking raw materials and finished goods in warehouses. Output devices like alarm systems provide visual and audio alerts for system anomalies like temperature spikes or pressure drops. Of course. Other output devices used in the plant are digital panel displays to show values from sensors and transmitters directly on the equipment, control valves and actuators to physically respond to programmable logic controllers known as PLCs to give instructions to regulate flow or pressure to prevent things from getting out of hand. Temperature control valves, pressure control valves are such things needed in these things. They uninterrupted power systems and data backup servers ensure continuous operation and business continuity. The software needs of the computer allow for regulating and optimizing operations. SCADA software allow real-time visualization, control and logging of process parameters, enable plant operators to intervene instantly in case of irregularities. PLC programming tools too are used as examples of software used. The softwares also consist of modeling softwares and simulation softwares such as Aspen, HYSYS, ChemCAD, and things used in order to optimize, design, and simulate plant processes. So, enterprise resource planning softwares are needed for inventory control, purchasing, finance, sales tracking, and human resources. For the computer network connectivity, instead of just choosing one, the smart thing to do is to use a mix of different types of connections where they make the most sense. This is the connectivity that will be used on the site. Ethernet LAN for where stability matters most. Wireless networking for flexibility and movement. and controller area network bus for machine to machine communications. Some parts of the plant involve machines talking to each other directly, like when an interlock system tells a valve to close instantly, or a drive needs to start in sync with a motor. This is where a CAN bus comes in. For the type of network design we would use, a layered hierarchical star topology that organizes the network separating field, control, and enterprise levels for enhanced cybersecurity and manageability will be incorporated. In conclusion, IT transforms how chemicals are produced. From instrumentation to enterprise planning, every part of the plant is digitally connected. And as we move forward, it is evident that the integration of IT will become even more crucial.